At the stroke of midnight on October 1st, 2025, NASA's official voice disappears. The agency's homepage displays a government shutdown notice just as 3I/Atlas, only the third interstellar visitor ever detected, enters its once-in-a-lifetime window for Mars observation. Public data streams go dark at the precise hour the cosmos delivers its rarest messenger, leaving only European orbiters and silent American eyes tracking a comet millions of kilometers from home. Was this outage a perfect bureaucratic storm? Or something more sinister when the stakes are this cosmic and the silence is complete? What are we seeing? And how does anyone separate coincidence from cover-up? The clock has started, and the evidence is about to be examined. A rare visitor from beyond our solar system does not wait for human calendars. In the pre-dawn hours of October, as the world's most powerful space agency falls silent, a fragment of another star's debris cloud crosses Martian orbit. 3 times in recorded history, astronomers have confirmed an interstellar object passing through our neighborhood, each arrival separated by years, each one a statistical outlier in a universe of repeating patterns. The odds are staggering. Billions of comets and asteroids shaped by our sun orbit predictably, yet only a handful ever trace a path that cannot be explained by any known planet or belt. The value of this moment is not measured in press releases or trending hashtags. It is measured in the way light bends through a foreign coma, in the chemistry that betrays a birthplace far colder or more violent than anything in our system, in the chance to watch a true outsider interact with a familiar planet. For a brief window, Mars, usually a backdrop for robotic explorers, becomes a solar system's best observatory. From its vantage point, the geometry is perfect. The visitor's path sweeps within 30 million kilometers, close enough for orbiters to track subtle changes in brightness, color, and speed, yet far enough to avoid any risk to hardware. The world scientific community knows what's at stake. Every previous interstellar object, Oumuamua in 2017, Borisov in 2019, left behind more questions than answers. Oumuamua tumbled out of sight before anyone could agree on its shape or even its true nature. Borisov, though more conventional, still challenged comet models with its composition and speed. Now, with a third candidate, the opportunity to compare, to test, to challenge old theories is within reach. The timing is razor-thin. The Mars window opens for only a week, with closest approach on October 3rd. After that, the comet slips toward the sun, lost in the glare, unreachable by even the largest telescopes on Earth. For planetary scientists, a single night's loss can erase a year's planning. A missed spectrum, a gap in the light curve, a failed pointing sequence. Each one narrows the margin for discovery. The stakes are not just scientific. In a world where information travels instantly, the absence of official updates creates a vacuum. Rumors multiply. Questions about what is known, what is being hidden, and who controls the story become as urgent as the data itself. The silence of a shutdown is not just a bureaucratic oddity. It is a stress test for public trust in science. The next 7 days will decide whether this rare encounter becomes a milestone of discovery or a chapter of missed chances and speculation. July 1st, 2025, a new object appears in the nightly search logs of the Atlas survey in Chile. Its orbit, calculated from a handful of early positions, refuses to close. Each new measurement stretches the curve further from the sun, hinting at a visitor not bound to any planet. Over the next 3 months, observatories across the globe feed in data, right ascension, declination, photometric points, until the trajectory is pinned down. The result, a hyperbolic path inbound from interstellar space, heading toward the inner solar system. October 1st to 7th, the Mars observation window opens. For exactly 1 week, the geometry lines up. The interstellar object sweeps through a corridor just 30 million kilometers from Mars, about 0.19 astronomical units. Mars, usually a silent outpost for robotic explorers, becomes the best seat in the solar system. Orbiters and landers adjust their schedules, prioritizing observation slots, ready to catch whatever signatures this outsider might reveal. The window is tight. Miss it, and the opportunity vanishes for decades. October 3rd, closest approach to Mars. The object passes at its minimum distance, a point source of light skimming the red planet's sky. No telescope on Mars or Earth can resolve the nucleus at this range. What can be measured are changes in brightness, subtle color shifts, the shape and extent of the coma, and any hint of unusual chemistry in the light it reflects. Every second counts. Each observation adds a line to the growing ledger of interstellar encounters. October 29th to 30th, perihelion. The comet rounds the sun at a distance of 1.36 astronomical units, about 204 million kilometers. At this point, the object is lost in solar glare from Earth's perspective. Mars has already lost its vantage. Only spacecraft positioned far from the sun's blinding light, like ESA's JUICE at Jupiter, have a shot at catching the peak of outgassing and activity. 4 ground-based astronomers. The wait begins. Late November to December, the object reappears from behind the sun. Telescopes on Earth now clear the solar conjunction, scramble to reacquire it. The light curve resumes. Spectrographs hunt for lingering traces of exotic chemistry. Each new data point is checked against predictions, searching for any sign that this visitor breaks the rules written by the first 2 interstellar objects. The timeline closes not with press release, but with a checklist. Discovery, Mars window, closest pass, perihelion, reappearance. Every date stamped, every distance logged, every observation ready to be verified. Inside the Mars science community, every asset and operator finds their role defined by the clock in the sky. ESA's campaign order goes out first. Mars Express and the ExoMars Trace Gas Orbiter are both tasked for the week, with their science leads at ESOC and ESTEC clearing schedules for high-cadence comet tracking. The HRSC and CASIS teams load new pointing commands, each sequence calculated to maximize coverage as 3I/Atlas sweeps past at 30 million kilometers, a distance that turns even most powerful camera into a glorified photon counter. On the NASA side, the Mars Reconnaissance Orbiter's HiRISE and CRISM teams receive last-minute observation windows, their requests logged by the project office, but held behind a firewall of legal silence. MAVEN's IUVS group pivots from atmospheric studies to cometary UV missions, working from pre-approved contingency plans. The Red Watch crew, NASA's term for the skeleton staff authorized to keep flight operations running, spend the early hours of October 1st confirming telemetry, cross-checking instrument health, and logging every command twice. They're the ones who stay on shift when the rest of the agency is furloughed, their names absent from press briefings but present in every operations log. Across the globe, the Chinese Tianwen-1 team at BACC and the UAE's Hope Mission controllers at MBRSC joined the campaign. HiRIC, MOMRIC, YXI, all high-resolution imagers are assigned to grab as many astrometric and photometric points as bandwidth allows. Each approval is routed through national science boards. Each exposure is a small gamble on weather, spacecraft health, and the unpredictable brightness of an interstellar visitor. On the ground, citizen astronomers like Maria Rubio, whose backyard discovery of a light curve anomaly first drew attention to Atlas's odd behavior, watch from afar, submitting real-time measurements to the Minor Planet Center. Their data, though less precise, fill gaps left by institutional constraints and reinforce the sense that no single agency owns the sky. Every observer, from ESA's operations directors to the Red Watch's overnight crew, works within the same razor-thin margin. 1 week, 1 chance. No guarantee of a second look. The infrastructure is global. The protocols are strict, and the human element, silent, mostly invisible, remains a common thread running through every data point that will outlast a blackout. At precisely 12:01 a.m. on October 1st, the Anti-Deficiency Act asserts itself with the force of federal law, shutting down NASA's public voice in a single sweeping motion. Every digital channel, websites, mission blogs, social media feeds, press offices, and automated news tickers fall silent. The statute, born out of a need for fiscal restraint rather than any cosmic agenda, prohibits federal agencies from obligating funds beyond what Congress has approved. The language is blunt. No money, no work, unless that work is essential to protect life or property. For NASA, this exception carves out a narrow corridor. Flight operations, those vital to safeguarding billion-dollar spacecraft and the data they gather, are allowed to continue, but only behind a firewall of silence. The Mars Reconnaissance Orbiter, MAVEN, and every other U.S. operated probe remain fully functional, their commands relayed through protected circuits, their telemetry flowing to mission control. Yet outside those walls, the blackout is total. Hundreds of furlough notices are dispatched to inboxes overnight. Outreach teams, education specialists, and public affairs officers are locked out of their accounts, forbidden by law from posting so much as a status update. The Red Watch crew, classified as accepted personnel, work through the shutdown under strict contingency plans. Every shift documented, every handover notarized, every action logged. The firewall is absolute. Data are archived, not shared. Health checks are performed but not announced. Even the most routine milestones, pointing sequences, instrument calibrations, data downlinks, are recorded in internal logs, invisible to the outside world. The official website banner is stark. NASA is currently closed due to a lapse in government funding. For those outside the agency, the effect is immediate and complete. No new images, no press briefings, no live commentary as an interstellar object brushes past Mars. The silence is not a glitch, nor is it a deliberate attempt to conceal. It is a direct outcome of legal code enforced by shutdown protocol that draws a hard line between the mechanics of planetary discovery and the story told to the public. The data continue to flow, but the narrative, at least for now, remains suspended, paused by statute rather than by science. For 7 days, the world's sharpest telescopes orbiting Mars become photon counters aimed at a single unresolved point. Every asset, ESA's Mars Express, ExoMars TGO, NASA's MRO and MAVEN, China's Tianwen-1, UAE's HOPE, works from pre-approved scripts, logging astrometry, broadband photometry, and if luck allows, a faint trace of gas in the coma. The nucleus itself remains hidden, smaller than a pixel, no matter how long the exposure. What comes back are light curves, brightness rising and falling with the object spin, colored data hinting at ice or dust, spectra chasing the faintest signature of carbon, water, or something stranger. Each measurement is a single data point waiting to be stitched into a narrative only after the blackout lifts. Outside the mission archives, the vacuum of official updates becomes its own kind of signal. Social media threads fill with speculation, some reasoned, some wild. Screenshots of ESA's last pre-shutdown blog post circulate alongside grainy plots from amateur photometry. Hashtags trend, hashtag Mars window, hashtag Atlas blackout, hashtag 3I or not 3I. Rumors multiply in the absence of detail. Some claim the silence hides a discovery, an anomalous spectrum, a trajectory that doesn't fit. Others insist it's just bureaucracy at work, a shutdown with unfortunate timing. The observational ceiling is clear. No camera at Mars can resolve the nucleus. No spectrometer can pull out more than the brightest gas lines, and only if the coma flares. Photometric data, astrometric positions, and low signal-to-noise ratio spectra are the full extent of what the hardware can deliver at this range. Every missing update, every unexplained gap becomes fuel for new theories. The rumor life cycle is short and relentless. A single ambiguous post can spark hundreds of replies, each one further from the facts on file in the mission logs. As the week wears on, the ledger fills with raw numbers, but the story outside the firewall is shaped by uncertainty. The next phase, sorting natural anomaly from narrative invention, will depend on how these fragments hold up when the blackout ends and the evidence goes public. 6 explanations compete for the ledger of what happened as the Mars window closed under silence. The first, and by far the most likely, is bureaucratic coincidence, a government shutdown timed by fiscal calendars, not by cosmic events, intersected with a rare but natural encounter. The second looks to the environment, solar wind or a Martian atmospheric anomaly interfering with data, a blip that could mimic a gap in coverage. Third is the speculative outlier, an unusually massive or metal-rich nucleus, the kind that would light up a spectrum or bend a trajectory in ways no comet from the Sun's family ever has. The fourth, black budget data capture, leans on the idea of classified science. Operations running in parallel, logged in places the public cannot see. Fifth comes a third-party intercept, technology beyond any known agency, a scenario with no evidence and no precedent. The sixth and most extraordinary is engineered artifact, an object built, not born, crossing the solar system under a disguise of dust and ice. Each step along this chain demands more proof, more evidence, more rigor. The evidence checklist is built for audit, not argument. Start with minor planet center orbital updates, hyperbolic elements, eccentricity, and velocity posted in public logs. ESA's Mars Express and ExoMars TGO data drops, raw images, spectra, pointing logs, and exposure times, all archived in the Planetary Science Archive. NASA's post-shutdown archives. Every command, every downlink, every gap explained in the mission logs. Post-conjunction light curves and spectra from ground-based telescopes cross-checked against predictions. Consistency across agencies, Mars, Earth, and Jupiter, means a smooth hyperbolic orbit, ordinary cometary volatiles, and no unexplained accelerations. A smoking gun would be a Doppler anomaly, a trajectory that refuses to fit, or spectral lines that defy known chemistry. Anything less is noise, not signal. The standard for anomaly is strict. Coherent Doppler or trajectory deviations, non-cometary spectral lines, or datasets that cannot be reconciled across independent observers. Anything that survives this gauntlet moves from rumor to record. The rest, gaps in the light curve, missing images, ambiguous spectra, are the normal scars of a campaign run at the edge of what is possible, not evidence of suppression. The evidence, when released, will decide which story holds. Throughout the 7-day blackout, Mars-based assets like the European Space Agency's Mars Express and ExoMars continued their campaigns, while NASA missions remained operational but silent by law. No credible evidence emerged of interference beyond the documented shutdown protocols. Yet the absence of real-time data fueled speculation, highlighting how routine policy and rare cosmic events can collide to amplify rumors. The evidence checklist remains. The European Space Agency's published Mars data, minor planet center orbital updates, and NASA's post-shutdown logs will confirm or refute any anomalies. As of now, all publicly available data show a smooth hyperbolic trajectory and ordinary cometary behavior. Some questions about possible anomalies or classified findings remain unanswered until further releases. This episode tested scientific transparency and public trust. Silence does not equal suppression, but the records, not the rumors, will decide what history remembers. When the cosmos delivers its rarest messengers, humanity's response reveals more than just our scientific capabilities. It reveals how we handle uncertainty, how we build trust, and whether we can distinguish between the extraordinary and the merely unexplained. November 15th, 2025, 9:47 a.m. Eastern Standard Time. The European Space Agency breaks the silence first. A press conference at ESOC headquarters in Darmstadt streams live across every major platform. Dr. Helena Kovacs, lead scientist of Mars Express mission, steps to the podium with a thick folder of printouts and a tablet displaying what will become the most analyzed spectrum of the decade. We have completed our preliminary analysis of 3I/Atlas during its Mars encounter, she begins, her voice steady but her hands trembling slightly as she pulls up the first slide. What we found challenges our current understanding. The room erupts. Cameras flash. Reporters lean forward. On the screen behind her, a light curve unlike anything seen in Oumuamua or Borisov. The brightness variations don't follow a tumbling pattern. They're periodic, precise, with a regularity that suggests not chaos but structure. A rotation period of exactly 6 hours, 14 minutes, and 3 seconds, consistent to within milliseconds across 4 days of observation. Natural objects, Dr. Kovacs continues, show variation, tumbling precession, irregular outgassing. This object shows none of that. It spins like clockwork. The second slide appears, spectroscopic data from ExoMars TGO. The expected signatures are there: water ice, carbon dioxide, simple organics. But buried in the noise, barely above detection threshold, is something else. A series of absorption lines that don't match any known cometary molecule. At first, we thought it was instrumental artifact, she admits. We ran the calibration sequences 3 times, but the signal persisted. These lines appear at wavelengths consistent with complex aromatic hydrocarbons, molecules we don't expect to survive in interstellar space, let alone remain detectable in a coma at this distance from the sun. A journalist shouts from the back, "Are you saying it's artificial?" Dr. Kovacs pauses. "I'm saying it's anomalous. We need more data to determine if these signatures are the result of exotic formation conditions or something else entirely." 6 hours later, NASA's post-shutdown data dump goes live. 16 terabytes uploaded to the planetary data system in a single batch. Every observation, every command log, every gap explained and time-stamped. Within minutes, amateur astronomers and professional researchers alike are downloading, parsing, cross-referencing. What they find sends shockwaves through the astronomical community. The Mars Reconnaissance Orbiter's high-rise camera, operating at the absolute edge of its capability, captured 37 frames of 3I/Atlas during closest approach. Each frame shows nothing but point source, exactly as expected at 30 million kilometers. But one frame, taken at 3:14 and 22 seconds universal time coordinated on October 3rd, is different. For a single exposure, the point source appears elongated, not by much, barely 3 pixels, but enough to be measurable. The elongation ratio suggests an object roughly 4:1 in aspect ratio, far more extreme than any known comet nucleus. Dr. James Chun, an imaging specialist at JPL who spent the shutdown under furlough, is among the first to analyze it. He posts his findings on the preprint server at 11:42 p.m. that same night, his analysis running to 47 pages of statistical modeling and error analysis. His conclusion: the probability that this elongation is due to instrumental artifact, seeing conditions, or statistical noise is less than 0.3%. If this detection is real, 3I/Atlas has a shape consistent with either a highly unusual natural fragment or design structure. The paper goes viral within hours. By morning, it has been downloaded 400,000 times. November 18th. ESA's JUICE spacecraft, nearly 800 million kilometers from the Sun in its journey toward Jupiter, provides a final piece of the puzzle. During the perihelion passage, when 3I/Atlas was lost to Earth-based observers in the solar glare, JUICE had the perfect vantage point. Its narrow-angle camera, designed to study Jupiter's moons, was repurposed for a high-risk, high-reward observation campaign. The images arrive as compressed data package, transmitted across the solar system at glacial speeds. When the science team decompresses them, 3 frames show something impossible to dismiss. At perihelion, when comets typically reach their peak activity, 3I/Atlas did something no comet has ever done. It stopped outgassing. The coma, visible and measurable for weeks before and after, vanished completely for a 47-minute window at closest approach to the Sun. No dust tail, no ion tail, just a bare nucleus reflecting sunlight like polished metal. Then, as suddenly as it stopped, the outgassing resumed, the coma rebuilt itself, and 3I/Atlas continued on its hyperbolic trajectory toward the outer solar system. Dr. Yuki Tanaka, JUICE mission scientist, summarizes the observation in a terse 2-sentence statement released to press. "We observed a complete cessation of cometary activity during peak solar heating. This behavior has no natural explanation within current comet models, but it's the trajectory data that ultimately forces the scientific community to confront the impossible." When astronomers from the Minor Planet Center, ESA, NASA, and independent observatories combine their astrometric measurements, positions accurate to milliarcseconds across 4 months of observation, they find something the early predictions missed. The orbit isn't quite hyperbolic. It's close, eccentricity of 1.0003, well above the parabolic threshold. But when they model the sun's gravity, account for planetary perturbations, factor in radiation pressure and outgassing forces, the numbers don't close. There's an anomaly, small but persistent, an acceleration of approximately 2.7 millimeters per second squared, directed not away from the sun like radiation pressure would cause, but along the object's velocity vector. The acceleration appears in 3 independent datasets. It cannot be explained by outgassing because it persists even during the perihelion blackout when no outgassing occurred. It cannot be explained by measurement error because the signal is coherent across observatories on 3 continents. Dr. Avi Loeb, the Harvard astronomer who famously suggested Oumuamua might be artificial, publishes an op-ed in Nature on November 22nd. The headline, "When Evidence Demands We Ask Uncomfortable Questions." For years, he writes, we have searched for signs of extraterrestrial technology by listening for radio signals and looking for megastructures around distant stars. But perhaps the evidence we seek doesn't announce itself with fanfare. Perhaps it simply passes through, silent and ancient, leaving only the faintest trace in our data logs, a trace we're now obligated to investigate. December 3rd, 2025, a radio astronomer at the Parkes Observatory in Australia, running a routine survey of the southern sky, picks up an anomalous signal at 1.42 gigahertz. The hydrogen line, nature's most common frequency, and the wavelength SETI researchers have monitored for decades. The signal lasts for 11 seconds. It's narrowband, far narrower than any natural emission, and its source, when the coordinates are traced back, aligns to within the error margin with the projected position of 3 I/Atlas, now 2.1 astronomical units from Earth and fading fast. The astronomer, Dr. Sarah Okonkwo, triple-checks the calibration before sending an encrypted message to the SETI Institute. Possible technosignature. Correlation with interstellar object. Request immediate follow-up. Within 48 hours, every major radio telescope with a view of the southern sky is pointed at the coordinates. The Green Bank Telescope, Meerkat, the Australian Square Kilometre Array Pathfinder. They listen for 3 days straight. Nothing. The signal does not repeat. If it was real, it was a single pulse, a greeting, a diagnostic, or perhaps just the electromagnetic equivalent of a door closing as something ancient and unknowable finished its pass through our solar system and continued into the dark. December 10th, 2025, a joint statement from NASA, ESA, the International Astronomical Union, and SETI organizations worldwide. The astronomical community has completed preliminary analysis of the interstellar object designated 3 I/Atlas. Observations reveal several anomalous characteristics, including unusual shape, atypical cometary behavior, and trajectory deviations not fully explained by natural forces. While these anomalies are significant, we emphasize that anomalous does not mean artificial. Natural processes we do not yet understand may account for these observations. Further study is essential. We are coordinating a comprehensive follow-up campaign as 3 I/Atlas continues outbound. However, given its velocity and distance, our window for detailed observation is rapidly closing. We encourage scientific rigor, healthy skepticism, and continued analysis. Extraordinary claims require extraordinary evidence. What we have now are extraordinary questions. By late December, 3 I/Atlas is beyond the orbit of Mars, moving at 33 kilometers per second relative to the Sun. Ground-based telescopes lose it against the background stars. Space-based infrared telescopes track it for a few more weeks before it fades below detection threshold. The last confirmed observation comes on January 8, 2026, from the James Webb Space Telescope. A single frame, 600 seconds of integration time, showing nothing but a faint infrared glow, thermal emission from a cold nucleus warmed briefly by its encounter with the inner solar system. Then it's gone, carrying its secrets into the void between stars. The data remain. Thousands of observations, terabytes of measurements, a trail of evidence that will be analyzed and debated for decades. Some scientists argue for natural explanations, exotic formation conditions, unusual composition, coincidental timing. Others argue the evidence points towards something designed, tested against the crucible of interstellar space, briefly visiting our star before continuing to destinations unknown. In the years that follow, 3 more interstellar objects are detected passing through the solar system. None show the anomalies of 3 I/Atlas. All follow predictable hyperbolic orbits. All display normal cometary behavior. All fade quietly into history as fascinating but unremarkable visitors, which makes 3 I/Atlas the outlier, the exception, the case that doesn't fit. Was it natural? A fragment of a destroyed exoplanet carrying complex chemistry through the galaxy? A comet born in conditions so alien that its behavior only seems designed? Or was it something else? A probe, a scout, a message in a bottle cast between stars, timed to arrive during a government shutdown that guaranteed its closest approach would occur under a veil of bureaucratic silence? The shutdown lasted 7 days. The receipts, when finally released, showed exactly what the protocols demanded: operational spacecraft, archive data, legal compliance. No conspiracy, no cover-up, just unfortunate timing. But timing that allowed something to pass through our solar system with minimal real-time scrutiny. Timing that kept the most powerful space agency in the world silent during the most significant close approach. Timing that, if you wanted to slip through unnoticed while still leaving evidence for those patient enough to look, would be absolutely perfect. On January 15th, 2026, Dr. Helena Kovacs gave a final interview about 3I/Atlas. The reporter asks the question everyone wants answered. Do you think it was artificial? She pauses for a long moment, choosing her words carefully. I think, she finally says, that the universe is under no obligation to make sense to us. I think we've barely begun to understand what's possible out there. And I think that whether 3I/Atlas was a rock or machine matters far less than what it represents. Proof that we're not isolated. The galaxy sends us visitors. Some might be debris. Some might be emissaries. Our job isn't to guess. It's to watch, to measure, and to be ready when the next one arrives. Because there will be a next one. And maybe next time we'll be listening when it speaks. In a secure server farm in Maryland, the complete dataset for 3I/Atlas sits in the NASA Planetary Data System, publicly accessible to anyone with an internet connection. Every image, every spectrum, every anomaly, preserved for future generations, buried in the metadata of the final JUICE observation, the one showing the cessation of outgassing, is a timestamp that goes unnoticed for months. A graduate student at MIT, writing her thesis on interstellar objects, spots it while cross-referencing observation logs. The exposure was taken at 14:42 in 3 seconds Universal Time Coordinated on October 29, 2025. She runs the numbers out of curiosity, converting to Earth time zones, just to see what time of day it was from different perspectives. And then she stops. From Earth's perspective, accounting for light travel time, that moment, the precise instant when 3I/Atlas stopped behaving like a comet and revealed something beneath the ice, occur at 12:01 a.m. Eastern Standard Time on October 1st, 2025. The exact moment NASA went dark. She stares at her screen for a long time. It's probably coincidence. Light travel time calculations are tricky. The margin of error is significant. Probably. She saves the calculation, flags it for her advisor, and goes to bed. But she doesn't sleep well, because in the back of her mind, a question has taken root, one that will follow her through her entire career. What if the timing wasn't unfortunate at all? What if it was the point?